He will give us his second pedagogical lecture on hydrodynamics, integrability, and variational principles. I remind everybody that Sasha is giving a blackboard talk, so although he writes very clearly, I invite those of you sitting far back to move a little bit to the front so that you can see better. Sasha.
Okay, good morning, everyone. So let me remind you that at the end of the last lecture, yesterday's lecture, I mentioned three origins of hydrodynamic equations. One was due to the quick relaxations of everything except for locally conserved quantities, and that's the main hydrodynamics, the proper hydrodynamics. Another one was due to spontaneous symmetry breaking, an appearance of massless mode due to Goldstone's theorem. And the final one was a little bit cryptic. It was about the choice of states, of initial states. And this I'm going to clarify today, and this has something to do with integrability as well. As an example, I will start with the simplest possible integral model, in a sense, trivial integral model, which is free one-dimensional fermions. So topic today is few topics in one-dimensional hydrodynamics. And the topic one is hydrodynamics of free one-dimensional fermions. There is a little bit of confusion of terminology. When I'm saying free one-dimensional fermions, I actually mean non-interacting one-dimensional fermions. In principle, they can be in external smooth potential. So they're not necessarily, they can be confined, but it's important part that they do not interact with each other. So we will consider the dynamics of free Fermi gas at temperature equals 0. So to do that, we first should probably talk about the ground state. So ground state of one-dimensional fermions can be represented in the following way. Let me draw here the wave vector axis. And then if I have fermions on one-dimensional line from 0 to L with periodic boundary conditions, our eigenstates of the free Hamiltonian are just plane waves e to the ikx, which are characterized by discrete values of wave vector. And the separation between those discrete values is 2 pi divided by L. And we start with k equals 0, and then we fill the levels so that the lowest energy states with a given number of fermions is filling all states from minus k Fermi to plus k Fermi. Okay? So I'm using here momentum p and also wave number k, which is differed just by h bar by Planck's constant. And for now, I will keep Planck constant to show which effect is quantum, which is classical. But I will put mass of particles equals 1. So for example, the mass density of particles is the same as the particle number density. So mass of individual fermion is 1. So let me calculate first the density of the fermions in the ground state, which is characterized by Fermi wave vector. And that's done very easily. We just take integral from minus k Fermi to plus k Fermi of dk divided by 2 pi. And that is k Fermi divided by pi. So k Fermi and the background density of fermions are related by this simple formula. It's also easy to calculate the volume density of energies. This is density per unit volume. You just have to take the same integral over all field states with the same measure dk divided by 2 pi, but now taking the energy of the fermions. In principle, what I'm talking about can be generalized for arbitrary dispersion, but for now I will be dealing with non-relativistic hydrodynamics with quadratic dispersion. again, it should be, and probably I need h bar k squared because I promised to keep h bar for some time. Okay? So this is p squared divided by 2m, but m is 1, so that's why it's just this quantity. And it's very easy to calculate this integral. It's h squared k Fermi cube divided by 6 pi. So this is the energy density of the ground state per unit volume. And we can compare these expressions and express the energy in terms of density, obtaining h squared pi squared over 6 rho cube. So what we just did is we derived equation of state for free fermions. So this is equation of state. It relates the energy density with the density of fermions themselves. Okay? Any questions so far? Okay. Then some little exercise. And the exercise is the following. We start with a very well-known thermodynamic relation, dE equals minus PdV. Remember that I'm in 0 temperature, so I really don't need the other term. And then I'm saying that the energy is the volume density. I'm considering uniform state multiplied by volume. And volume can be written as number of particles divided by density. So the exercise is to derive that it follows from this expression that pressure actually equals density multiplied by the derivative of the equation of state with respect to density. This epsilon rho means that I have to take this and differentiate it with respect to rho minus epsilon. That's an exercise. This is purely thermodynamic exercise. And as a result, we obtained pressure of one-dimensional fermions equals h squared pi cube divided by 3 rho cube, which you can also call equation of state. So basically, you can go from pressure to energy, etc., etc. Let me stress right now that this pressure is due to the Pauli principle. It's due to the fact that when I'm filling my states, these are fermions, and I cannot put them all to k equals 0 state. So I have to give some kinetic energy to those fermions. So although it looks like internal energy, this looks like internal energy of the Fermi gas, the origin is that this is just purely kinetic energy due to the Pauli principle. So going a little bit ahead, if I take limit h bar going to 0, quasi-classical limit, then this pressure disappears. And this is nothing interesting is left. So what I'm going to talk about quasi-classical limit, but when I mention quasi-classical limit, this is non-trivial quasi-classical limit. It's not just h bar going to 0, but it's simultaneous limit of h bar going to 0 and density going to infinity in such a way that h bar rho is fixed. If I do limit of this type, then you can see that h bar rho will become of the order of unity in terms of h bar, and it will be comparable to velocity, and therefore in hydrodynamic equations I have to use both velocity and density. Otherwise, density just disappears from equation of state. Okay? So what I'm going to do next is I'm going to promote these thermodynamic equations to hydrodynamics. By this I mean, so I will do it in a naive way, and it's like a shortcut, and then we will do it in several other ways. So you will have some kind of justification of all it. What I'm saying is that just let's introduce, so I have a density of one-dimensional fermions. Let's suppose now that this density is a function of space and time, which is slowly changing. And I want to introduce also momentum density P of x and t. Now I will really have confusion, so let me use J instead of P, so not to confuse it with pressure. And this J I will write as product of rho times V, and V will be as well as rho slow function of x and t. And what I'm going to write is, first I'm going to write the conservation of mass in the form of continuity, in the form of continuity equation, plus dx rho v equals 0. But then I will also write dt v plus dx of v squared over 2 plus h squared pi squared rho squared over 2 equals 0. Okay. So any questions so far? Say it again. Oh yes, these are spinless fermions. Yeah, nice comment. Yeah, these are spinless fermions, no extra degrees of freedom, just one-dimensional spinless fermions. Yes. Yes, that's right. So what I'm talking about is good for any spectrum of this type, where you have both right and left Fermi surface. Then some things change, but roughly the derivation can be continued. If you have chiral fermions, it's a little bit different story because of some anomalies, but it can be also done. So let me just illustrate how this appears, why coefficient here is 1/2. Remember that in the right-hand side of earlier equation, I generally have -1 over rho dx pressure, right? So if I substitute this here, then I get -1 over rho h squared pi squared, and then dx of rho cube gives you rho squared dx rho. One of rows cancels, and then you notice that this is minus dx of h squared pi squared rho squared divided by 2, and this is the origin of this term. Generally, the quantity which enters here is chemical potential, which is also related to by thermodynamic identities to the epsilon or to p, so you can actually always find it. Okay? Vector of pi, where is? Oh, yes, that's right, sorry. This is pi squared. Thank you. Okay. So this is very remarkable system of equations. What you can do is you can do the following trick. Let's introduce the quantity. Well, basically you can already see it from here that if I add these equations with fine-tuned coefficient, then you will see that this is v squared, this is rho squared, and this is cross product rho times v. So if you add it with good coefficient, this will be full square, complete square. Okay. So let's do that. Namely, we do it in the following way. We'll introduce variable u, either right or left. You will see the explanation why this is called, which is v plus minus h pi rho. Then it is very easy to show by just adding this equation together, by multiplying this equation by h bar pi and adding to this one or subtracting, that both of these u's, right and left, with plus and minus, satisfy the same equation ut plus ux equals 0. Again, the index here means partial derivative. Okay? So what we see is that instead of two coupled equations for rho and v, I can actually represent this hydrodynamics in terms of the two separate variables, right and left. An equation both for right and left is the same and completely independent from each other. Okay? So I separated my hydrodynamics into right and left moving modes, as can be shown. This equation is very well known. It's called Riemann-Hopf equation. It can be solved by method of characteristics, generally a little bit implicit solution, but basically for any initial profile of U, we know the solution. Yeah, you can do that also. Yeah. Well, not really. Well, if you make time imaginary, I will come to that. Then it's basically solved in terms of analytic functions. But even this one can be just solved directly. So basically, the general solution is something like this: U equals initial U of x minus ut. If you take any initial profile and solve this implicitly, this is implicit. Solve this with respect to U, you will get U of xt, which solves this equation. Exercise, please check. Yes. Why right and left? Because as you can see here, suppose that velocity is small here, then this is for right variable it's plus pi, and for left it's minus pi, and the background density is rho 0, so this basically is positive for right and negative for left, and if it's positive, it means it's propagating to the right. If it's negative, it's propagating to the left. So, but this is okay. So I'm now going to show some semi-classical picture of what's going on, and you will see why it's right and left, and what I mean by that. Any questions? Fluid particle. Huh? I have one-dimensional fermions, so I will take some piece where there are many fermions, and I'm looking at the motion of this piece. So the same as before. But let me now go to semi-classical or phase space picture of what's going on. Yes. In semi-classical limit, no, not really. The pressure has h bar here. Yeah, that's true. But what, as you can see, right. But this is like a common factor. This additional infinity is a common factor. So you basically can always rescale it into time dependent. So this is not so important. Important part is that to have non-trivial hydrodynamics, I want to use both velocity and density, and therefore this term should be of the same order. Otherwise, you just forget about it, and it's not interesting. So these terms of the same order, and for that, h bar times rho should be of the order of velocity, generally. Otherwise, it's not interesting dynamics. So, okay, so semi-classical picture. Let me consider one particle phase space. So this is x, this is k. And then the ground state, which I was talking about, I can represent as something like this. This is minus k Fermi. This is k Fermi. The plane wave state I was mentioning is something like this. It has a very specific value of momentum, but absolutely uncertain in x. So you basically have to fill this with this kind of lines. Okay? This is one way of representing it. Of course, you can make this state also as a slated determinant of different coherent states. The important part is that each of those should take the volume 2 pi in this phase space. 2 pi h bar in px, but 2 pi in kx space. But what I'm going to talk about now is I'm going to talk about perturbed states. This is like really equilibrium lowest energy state representation. What I'm going to say is something like this. Let's assume that I have the following picture. I have some domain in a phase space which is filled by fermions. So my local picture at given x is that I have the lowest boundary k left and the upper one k right. And all states in between are filled with a separation 2 pi over L. But this k right and k left itself can change slowly in space and time. So this state is fully characterized by k right of x and t, and k left of x at t at any time in x and point of space. Okay? So this is a perturbed state of free fermions. The technical way to obtain this state is to act by some coherent, to form some coherent states out of slated determinants, but I'm not going to talk about it, just to look at this picture. So what I'm going to do now is I'm going to now write local density and local velocity in terms of this for this particular state. So basically I'm repeating the story there. So I'm saying that rho now is integral from k left to k right of dk over 2 pi, which is k right minus k left over 2 pi. Then the moment density should be integral of k left to k right dk over 2 pi, h bar k. And this is h bar k right squared minus k left squared divided by 4 pi. Okay. And I will write this as rho times v. And comparing with this, it means that I introduced velocity v, which is equal to, you basically have to divide this by this, k right minus k left cancels, so you'll have h bar k right plus k left divided by 2. This is velocity. Okay? So for this picture, it's very clear. The density is roughly this size between these two boundaries, and the velocity is the center of mass of those. Okay? And now the only thing which is left is, for example, to calculate the energy density, and this is now integral from k left to k right dk over 2 pi multiplied by k squared over 2 h bar squared. And I obtain h bar squared k right cube minus k left cube divided by 12 pi. Okay. So this is not an independent quantity because I have only two quantities which fully characterize the state, k right and k left. So, and I already have rho and v defined. It means that everything else that I have, I can express in terms of rho and v. Okay? And to do it, the quickest way to do that is just to say that let's introduce hk right as v plus h bar pi rho, and h bar k left as v minus h bar pi rho. And these are our u right and u left, which we introduced before. And this again shows you why I'm talking about the right and left. So basically I'm saying that this quantity u right is essentially this k right up to h bar. And of course, if you have particle here, it will move to the right with momentum k, and particle here moves to the left. The right and left are, I mean, in principle, you can have the state like this, where both k right and k left are positive, so they both move to the right. But relative to the center of mass, one moves to the right, one to the left. That's why I call it right and left. Okay. So having now those formulas, I can substitute them here and express epsilon in terms of rho and v. And of course, I obtain the same formula as before, h bar squared pi squared over 6 rho cube. Plus rho v squared over 2. And this gives me the density energy per unit volume. Okay? And of course, working this in terms of hydrodynamics, I obtained back this system of equations. That's right. Yeah. So basically, what I said is that let's forget about possible gradient corrections. Let's look at the zero-order hydrodynamics. But in zero-order hydrodynamics, if I have density and velocity which change very slowly in space and time, then locally I have more or less thermodynamic equilibrium, and I just extract formula from thermodynamic equilibrium for the energy density and use it in my Hydra equations. This is by promoting, I'm just saying that I'm using thermodynamics, but I'm just saying now all quantities depend solely on space and time. In this particular case of free fermions, there's a really very nice shortcut derivation. Even if you don't know anything about hydrodynamics, it's very easy to write equation for this k right? Because these are free fermions, these are non-interacting fermions. So if you take fermion here at the boundary in your phase space, this is some particular fermion here, and you see that this fermion will just move to the right with velocity h bar k right. Well, you have to divide by mass, but remember that mass is 1. Right. Just a second, let me go a little bit ahead. So what I'm saying is that let's start with the quasi-classical state, which is defined by this. Then what happens that every fermion here will move to the right with a velocity proportional to k. And every fermion here will move this way. So basically all fermions move with velocity proportional to the k to the right. So you can in principle think about the evolution of this distribution function, and then you will obtain Boltzmann beta or beta Boltzmann equation with Professor Moore mentioned yesterday, except that v, which in general for integral models is a complicated function, in this particular case is just equal to k. It's very simple. I will actually write it in a second. But what I'm saying is that just looking at this picture, you can see first of all that the density is constant here, and this is a shear motion. So what will happen is that if density is constant here, and it's equal to 1 over 2 pi, then it will stay constant. So if I started with this state, which is characterized by just 2 lines, the boundaries support of this domain, of the density in the phase space, then this line will just evolve. And because these are non-interacting fermions, the fermion sitting here will, first of all, keep being the boundary fermion, and secondly, it will move to the right. So what I can write is that if I sit on that fermion, then k right doesn't change. So how I write that? I'm just saying that if I take h bar k right time derivative plus h bar k right times space derivative times h bar k right, it should be 0. Remember, so what I wrote here is the operate dt plus h bar k right dx applied to h bar k right. This is our dt operator introduced before. It just tells you that if this is 0, it just means that k right does not change if you move together with the boundary, with fermion at the boundary of this domain. Okay? So even without all this promotion stuff and stuff like that, I can just write this equation right away. And if you see that, this equation is precisely ut plus ux equals 0 for u both u right and u left. And if you write it separately for right and left, and then take this equation and add them and subtract them, you will obtain hydrodynamic equations in terms of density and velocity. So instead of promotion here, you could just consider this semi-classical picture, write this equation directly because fermions are non-interacting, and then derive equations in hydrodynamic form from that. I'll talk about this in a second. Yes. it's nobody's fault. So if you have this system, this is the particular initial state. I will talk about this in a second again. Then fermion here is not interacting with any other fermion. So it moves to the right without knowing anything about the left boundary. So essentially what I'm doing here is I'm saying that from the point of view of motion of k right, I could also consider this type of distribution. I don't care about the lower boundary. This will still move to the right. And this will still move to the left. So this is exact for non-interacting fermions. So the reason they separated is because they're non-interacting. This is exact separation. We usually, even if they are interacting for small deviations from equilibrium, we usually can separate right and left moving modes. But that's approximate construction. This one is exact. This fermion here just does not know anything about everything else. It moves to the right. Okay? So what I'm doing here is that, in other language, if you have epsilon as a function of k, this is other epsilon, which is the dispersion, parabolic dispersion, and I have a feeling up to here that I'm saying that this is the right movers, this is the left movers, and this is the same story. Okay? I'm not sure whether I clarified it, but we can talk more. Okay. So we derived one-dimensional hydrodynamic equations for free fermions. In terms of density and velocity in a standard for hydrodynamics form, it's written as continuity equation plus Euler equation with a particular equation of state, with a particular chemical potential. In this particular case, we can actually derive it much more consistently and also in a way which in principle fits the generalizations for quantum systems. Yes? Right. So here, remember, I consider the true ground state from minus k Fermi to k Fermi, where basically system does not move macroscopically, right? So it's just basically v equals 0 in this case. Now, there are two ways. I did it straightforwardly using k squared over 2, but I also can say that I have Galilean invariance in my system with spectrum k squared over 2, and in Galilean invariant system, if I boost everything, it should be shifted by rho v squared over 2, the energy should. So this is a particular case of that one for velocity equals 0. True. This is for this one, right? So this can be written as dtv, which is first two terms, plus dx of h squared, pi squared, rho squared over 2 equals 0. Yes? I am doing the same thing because those are these equations. So this is the enthalpy term comes in Euler equation. This is not Euler equation. This is the splitting of both Euler and continuity equations into two, one right and another left equations. So you really cannot just say it should be enthalpy everywhere. And the reason behind this is I'm just saying that if you look at these fermions, that each point here moves to the right with velocity h bar k right. So the whole boundary here moves like this. So if I'm sitting on this point is not changing its momentum because fermions are not interacting, there are no forces. So it just moves to the right. So if I sit here, then I see that hk right does not change if I'm with this particle. So this equation just tells you that h bar k right does not change if I am moving with a particle with velocity h bar k right. Yes? Right. This is I took into account. Oh, this is from the very beginning when I just said that I will fill these states, not just put them in one. This is I've taken into account Pauli principle here of fermionic statistics. So this expression is quantum. It knows about h bar. If h bar is 0, no Pauli principle, epsilon is just 0. So this knows about Fermi statistics. That's a good question. Yeah, it's what I draw here. So if you take this point, it has momentum equals 0, so it's not moving. This point has momentum h bar k, so it moves to the right. This point moves to the right with double velocity. So this is like, it's called shear flow. So it's like this. Absolutely, because they're not interacting. If they were interacting, in principle, you can change momentum of particle by its interaction with other particles. But if they're not interacting, they just move with fixed velocity. This fermion does not know anything about anything else. If Fermi statistics is already taken into account by placing them in separate boxes. But after that, this fermion does not know anything about other fermions. It just propagates with given k. So what you see is that initially I fill this space with e 1 or 2 pi. And because this is just shear flow in this phase space, the density will still stay constant. Therefore, this type of profile will just be the same for some time. So it will still be characterized by sharp boundary between unfilled states and filled states. Okay? So this is the phase space picture. And this is the not phase space picture, but just purely space-time picture. I sort of integrated in the vertical direction, which I will do precisely and explicitly right now. So let's do somewhat different derivation. So let me talk about collisionless Boltzmann equation. So let me introduce f of px, which is the one particle phase space distribution function. One particle phase space distribution function. Which means that if I'm in xp space and I integrate this fpx over dp dx over the volume of this phase space, I will obtain the number of particles sitting there. So it's density of particles in phase space. So the number of particles is conserved, so particles do not disappear. And in Hamiltonian dynamics, the phase space volume is also conserved by Liouville's theorem, which means that this f does not change in time. df over dt equals 0. On the other hand, this equals to the explicit dependence on f on time, dtf, plus dependence of f through p and x. So I will have dp f p dot plus x dot dxf. And that equal to 0. Okay. This is called collisionless Boltzmann equation. If you have additional rare interactions of particles with each other, then you have to put here collision integral, which Joel wrote explicitly yesterday. So, which shows you that during the collision, particles actually can jump in phase space and change their positions. So, but if there are no collisions, this is just 0. And now let me assume that there is no external potential. Then p dot is 0, because this is a force acting on a particle, and if there is no external potential, no forces. And x dot is roughly p. Well, it's p divided by mass, but mass is 1. Okay? So what I obtain is the following nice equation. dtf plus dxpf equals 0. And you can recognize the better Boltzmann equation in the most trivial form when v, which Joel Moore used yesterday, is just p. Okay. It's the simplest possible. Okay? So this is collisionless Boltzmann equation. It's very general. So you can basically take any initial distribution f fermions. So you can, for example, this distribution. So you can take strip, then some piece field here, then individual particle here, anything you want. And then this distribution function will evolve according to this equation. This is exact. Okay? So now let me introduce moments of distribution function. So moments. With respect to momentum space, so I will introduce notation Fn, which by definition will be integral of, okay, I used dp over 2 pi, p to the power n, f of px. Okay? So notice that F0 is nothing else as what we call density. F1 is what we called momentum density, J. And F2 is, well, this is p squared. I use p squared divided by 2 for energy, so this is 2 epsilon. So first 3 moments are already the quantities which I introduced before. The next moment, F3, is already given by integral of p cubed, which is given by k Fermi to the fourth minus k left to the fourth for that particular distribution. This is still general. I did not assume anything about how particles are distributed in the phase space. And what I can do now is I can take this equation, multiply it by p to the power n, and integrate with dp over 2 pi with this equation. Okay? So what I obtain is the following nice equation. I obtain dt of Fn, the change in time of the nth moment, plus dx of the n plus 1 moment equals 0. Okay? Again, so far, no approximations, this is exact. So if I take n equals 0, 1, 2, 3, I obtain dt rho plus dx rho v. I just call my j rho v. This is just notation. Then I will have dt rho v plus dx of 2 epsilon. And then I have dt epsilon plus dx of 1/2 f3, etc. Okay? So I have infinite chain of equations like this one. These are particular examples. So for every n from 0 to 1, 2 to infinity. And they're all coupled. So for every equation, I have to introduce new moment, and for the new moment, I have introduced next moment, and so on and so forth. It's not possible to uncouple these equations in a trivial way. Okay? However, we can truncate this system to finite one if we assume particular initial state, which is pictorially described here. If I assume that my state is like this, then essentially it's fully characterized by k right and k left, which are only 2 fields. So I can express all these moments in terms of these 2 fields, and therefore I can express all these moments in terms of first 2, meaning rho and v. Okay? And this is the reason why that equation turns out to be a hydrodynamic equation, because it's a very particular initial state. So the formal exercise is the following, that let's assume that f of px is equal by the step function of k right of xt minus p minus step function of k left of xt minus p, which essentially I'm saying that this f is 1 between these 2 lines and 0 outside. Okay? So the exercise is that take this, substitute this into this equation, and show that it satisfies this equation if k right and k left satisfy those equations. Which is physically kind of obvious, but it's good to do this as a formal exercise as well. Okay. Any questions so far? Right. There is no such thing here, right? Well, so this is the most typical example of non-interacting, non-relativistic fermions with quadratic dispersion. So no interaction here. The surprise about XXZ is quite interesting. That one of the currents correspond to the energy density. But here it's just simple exercise. I'm not sure what I can add to that. In N. So one of those coincides with the previous one. Well, here, yes, but this is not, will not work for XXZ. Because for XXZ, this one is not this one. Yes, one of them coincides with the previous one, but here you have kind of this for everything. So this is much simpler. So you will not be able to truncate it this way. You can try to truncate it this way. You have to make some conjectures that your initial distribution such that one of these guys coincides with one of the previous ones. You'll probably truncate. I didn't really think about it too much. Does it correspond to a particular distribution? Will it stay in time the same way? I'm not sure. It's interesting. Yes. So this equation, so actually, let me come back to that because I have exercise for. I will ask you to generalize it to quantum picture, so it will be exercise. So and I will formulate what happens. So let me postpone this for just 1 minute. Yes. No, this is just because sometimes people define moments like Pn divided by n, then you will not have factor of 2. It's just a matter of convenience. So, yeah, no significance. Will be another factor. So will be no significance here. Okay, the next exercise is try to generalize all of this for fermions with arbitrary dispersion and presence of smooth external potential V of x. So exercise. Generalize to energy equals epsilon of P dispersion. I did everything for P squared over 2, for P squared over 2m. Well, you can do this for general one. And also in the presence of smooth potential V of x. Or even V of x and t, you can drive your system as well. So as long as this V of x is smooth on the scale of interparticle distances, you can generalize it easily. And now I have some few remarks. So the first remark is the following, that it's not as simple as I presented, because, and this is related to, I think, Sriram's comment, is that let's suppose that I started with some profile like this, semi-classical picture in a phase space, and I wait for some time. What I was basically saying is that this particle, because it is free, propagates with velocity proportional to k for this particular particle, and this particle propagates to the right with velocity k proportional to this wave vector, okay? So it's kind of obvious that in finite time, you will have picture like this. Okay? And from the point of view of equation for k right, which is ut plus ux equals 0, this is truly bad. Because if you really look at this picture, then u at this point becomes multiply valued. But you will not even get to this picture. If you start with this, and we start with initial condition for u as a function of x like this, then in a finite time, what you will have is you will have infinite gradient at this point. So at some time tc, you will have infinite gradient at this point. And if it's infinite gradient, that this equation is not defined anymore, not well defined. So this is ill-posed problem beyond time tc. If you just look at this equation, Riemann-Hopf equation, it develops shock wave singularity in a finite time. Okay? This is called gradient catastrophe phenomenon. And it happens in finite time. On the other hand, if you think about phase space picture of distribution of fermions, there is no problem with that. You just feel these states, don't feel these states. So this is some legitimate quasi-classical state of free fermions. Which means that this actually catastrophe is a problem of hydrodynamic description, not the problem of free fermions themselves. And if I really want to go beyond this gradient catastrophe point and to describe this profile, you see I already have 4 values of wave vectors which defines this state. So I should use something like 2 fluid hydrodynamics in this region, or maybe I should introduce the form of these lines indifferently. For example, I can take this point and put the rays and parameterize this curve in terms of the crossing here, and then I will have just one function which still describes this. So you can try to think about better descriptions. These descriptions in purely hydrodynamic way has a problem, has shock wave. But in principle, for free fermions, you can go behind it and define what's going on after that. This is some way of resolving gradient catastrophe here. So this is a hint that for this type of integrable systems, well, these are free fermions, this description is much more reliable. Because this is valid for long times, while this one breaks at some finite time. And this is a hint to this generalized hydrodynamics description that it's better to deal with the distribution of function in phase space. Okay, that's one comment. The next comment is an exercise. So far, I was drawing pictures and saying that this is semi-classical picture, but it would be nice to derive this semi-classical picture from purely quantum picture. And this is exercise, you can do that. And the way to do that is to introduce Wigner's operator. F operator of P, X, and T equal integral over Y of the Fermi field operator X plus Y over 2T psi of X minus Y over 2T e to the minus IPY. Okay? So what I'm doing here is I'm having annihilation and creation operators of fermions. The half sum of their arguments I call X, and this is my argument. And in the difference, I make a Fourier transform and introduce P instead. Okay. This is quantum operator. And the fermionic operator satisfies Schrödinger equation. Well, it's actually this equation. So what you can do is you can apply I dt to F. This is linear equation. So when you apply it here, this dt will act either here or here. There are 2 terms. And you replace one by this one, and you manipulate using Fourier transform and stuff like that, and you will derive the evolution equation for this F hat. And then the question will be of averaging this over some coherent states of that type, and then you will derive classical approximations. But this is the quantum analog of that collisionless Boltzmann equation, which I was used. Okay? Any questions? Okay. If there are no questions, let me give you some references, as I promised. Actually, the first reference is such that I think all authors are here in this integrability workshop, so you can ask them for details. So they were motivated by string theory, but if you drop this part, this will be about free fermions. Well, they understood it explicitly, so let me give you archive reference so it's easy to find. And this is 1993. And for more details, you can look up papers by L. Bettelheim, Paul Wiegmann, and myself. Both Paul and Eldad been here last week, I guess. And the short paper is in PRL 97.46.402. This is 206. Also, archive also 2006. And additionally, particularly for some refinement of free fermion evolution, including quantum corrections, this is a paper by Eldad and Paul. And this is PRP 84. 085 102 2011. Okay? So from this paper you will see that free fermions is not a simple problem at all. So it's the problem itself. Say it again? 085 102. This is 2011. So although free fermions look like a simple problem, but it depends on the observable or quantities that you want to consider. And if you consider complicated quantities, even for free fermions, the evolution is pretty involved. Okay, any questions? Yes, that's right, yeah. I was actually going to say that about Collisionless, including this one. Yeah, but this is right. All these equations are Hamiltonian, so you can write actually Hamiltonian and Poisson bracket, if you're talking about classical equations, and derive that from Hamiltonian formulation. Which is maybe not quite surprising, because you started from free fermions, which is definitely Hamiltonian system. However, these are exact equations, so they make sense, and they are Hamiltonian, and that's really helpful when you study those equations. I will mention this. I have time to talk about Collisionless model. So all this, actually I have it right here. So all of this has also, that's the last remark, which I will not write, but just say the generalization of the above for Collisionless-Sutherland model exists. Collisionless-Sutherland model is the model of interact particles, very special one. The phase scattering of those interacting particles is constant, so in a sense this is like a free fermions, and therefore the beta ansatz is particularly simple for that model, and that model reminds free fermions in many ways. The Collisionless model probably will be considered by Alexios Palachronakos in his lectures in detail. If I have time, I will talk about Hydra or Collisionless but I now want to talk about some unusual application of hydrodynamics, because you can think what this hydrodynamics is useful for, and I'm going to solve one problem where it is useful and provides you a simple shortcut to solution. Okay. So my next topic will be application of 1D Hydra to emptiness formation probability problem. And I'm not sure how detailed will be my coverage. What you can look for is that reference where I explain this in my Vishal lecture, which is a long time ago. 307. Okay. So to start with, let me define what is emptiness formation probability. Let's suppose that I have some system of particles interacting or non-interacting, doesn't matter for now because I'm just doing definitions. So which is characterized by the ground state, ground state of x1, xn, where I have n particles, on a line, say, with periodic boundary conditions. And then I will introduce the following object. Well, normalization factor. And then I integrate over dx1, dxn along the line of the psi j of x1, xn squared. If I integrate it over all space, I will get 1, obviously, because it's of this normalization factor. But what I'm going to do is I'm going to integrate it over xi in absolute value bigger than r. So this is my x. What I'm basically asking, what this quantity tells you, is that what is the probability that there are absolutely no particles between minus r and r? That all particles are outside. That due to some quantum fluctuations, the region is formed which is free of particles. Or in other words, the density of particles is 0 at this point. Okay? This quantity is called emptiness formation probability. And it was considered motivated by the fact that this quantity has especially simple multiple integral representation in integrable models. And Sergei Lukyanov, who is present here, calculated this quantity, some leading asymptotics of this quantity for XXZ spin chains. Much more complicated things that I'm going to do now. So what I'm going to do is I'm going to give you some shortcut, which generally is applicable not only for integrable systems and for any integrable systems, very general, but technically it's pretty complicated. So what I'm going to do to illustrate it for free fermions, that's easy. Generalization to other systems possible, but much harder. And many of them were not done. So this is like an open question. So what I'm going to do is I'm going to reformulate this question in, well, strictly speaking, this is a property of the ground state. In defining this, I use only ground state. I'm going to generalize it to dynamics. In principle, I can choose dynamics whatever I want, just so that the ground state is the correct one. But let me consider this problem for free fermions, and assume that hydrodynamics is what I wrote before, the quadratic dispersion leading to rho v squared over 2 plus rho cube type of energy. So I'm going to formulate this question in a dynamical way. I'm going to say that I'm watching this one-dimensional fluid, and it fluctuates due to the quantum mechanics, and ask what is the probability that this fluid parts and gives me the empty space from minus r to r at some time equals 0. Okay? the friend of mine suggested to call it quantum exodus problem. Okay, so what is the probability that rho of x bigger than minus r and smaller than r equal to 0 at time equals 0? What is the probability of that? Okay. I'm going to do it in steps, and we'll give you some minimal justification of each steps. So step 1, write down hydrodynamic equations for free fermions. And I will just rewrite system which I already wrote before. And now I drop h bar as well. We can restore it at the end. So both h bar and m equals 1 here. That's a step number 1. We already did that before. So step number 2 is, let me write the action variational principle which produces these equations. I do it in the following way. First of all, I will explicitly solve the first equation by parameterizing rho as rho 0 plus dxu, and parameterizing rho v as dtu with minus sign. This u is called displacement field. Essentially, I treat this as solid in some sense. Displacement field is literally how particle is displaced with respect to its initial position. And of course, if you take divergence of these displacements, you will get the increase of density compared to the background density rho 0. Okay? So it's very clear that if I substitute this into here, this is identically solved. Okay? So the only thing I have to do is I have to write the action in terms of u, so that if you apply variational principle to this action, you produce the second equation. And the action is given by s of u is given by minus integral dt dx 1 over 2 rho dt u squared minus rho epsilon of rho. Where epsilon of rho here is pi squared over 6 rho squared. Okay? So let me show you, let me just vary this action and show you that this equation is produced. Okay? Just simple exercise. I should leave it as an exercise. Actually, let me leave it as an exercise. Okay? So you have to remember, the only thing you have to remember is that when I write rho here, I essentially write this. It's rho 0 plus dxu. So there is only one variable here, one field, which is u. So I have to vary this with respect to u. I switch derivatives, get delta u multiplied by something, and that something will be exactly this equation. Okay? Okay, please study variational principle if you didn't. I will talk more about variational principles next time, but for the sake of time, let me leave this as an exercise. So minimizing this action, extremizing this action with respect to u gives you this equation. Okay? This is exercise. 3. Any questions so far? Step 3. Let me quantize this hydrodynamics. Yes? I stole it because, of course, it was written before many times. So, but there are more regular ways of doing that. Very often you just guess, and I'm going to talk about it in more detail when I talk about variational principles. If you think about it, this is nothing surprising here, right? Because this is kinetic energy minus potential energy. So it's like a mechanics. This dtu, remember, this is rho v squared, rho v. So what is written here is rho v squared over 2, which is kinetic energy of the fluid moving as a whole. And this is internal energy, which is, from fluid point of view, should be considered as potential energy, therefore it's minus. However, of course, from the point of view of its origin, this is kinetic energy of Pauli particles due to the Pauli principle. But from the point of view of mechanics, of continuous media, this is kinetic energy, this is potential energy. So this is a very standard action, kinetic energy minus potential energy. The tricky part was here, so that I already solved this using this displacement field parameterization. But this one is pretty obvious. Okay. Step 3, let me quantize. I'm talking about quantum fluctuations, so I really need quantum mechanics, so I really need quantum fluctuations. So let me quantize this and write that partition function equal integral over all possible evolutions of displacement field, functional integral, of e to the I s of u, where s of u is this one. Okay? So I quantized hydrodynamics. Well, quantizing hydrodynamics is a notoriously difficult problem. So of course there are simplifications here. First of all, it's one-dimensional, which makes it much easier than general hydrodynamics. And secondly, I actually, in my approach, I will not care about this measure because the subtleties of measure will give me corrections to the leading asymptotics for which I'm after. So I will claim that the subtlety of quantizing hydro is actually here, but this will not affect my result. Okay? One more thing which I probably have to say is that generally emptiness formation probability is defined for any R. It can be also defined on lattices, or say spin chains, or for particles jumping on a lattice. And this R can be anything in definition. Of course, what I'm after is for R much, much bigger than interparticle distance A. Only in this regime I suspect that I can deal with collective description of hydrodynamic description. Otherwise, it's really ultraviolet dependent and depends on the lattice model. What I'm going to do is I'm going to use hydrodynamics, which means I basically will have only chance to consider the large R asymptotics of my emptiness formation probability. By the way, any guesses? So how P of R behaves as R goes to infinity? Say it again? I don't hear at all. Should go to 0. That's definitely correct. How? How quickly? For those who don't know. Okay. One is some power law. Another is exponential. Okay. And typically, what people guess is that exponential decay, because if I ask you what the probability is that this volume of the air will become empty due to these thermal fluctuations, the answer will be exponential in volume. Okay? So usually people get exponential, but this is quantum problem, so it's actually will be this. It decays as Gaussian as a functional part. And we will see that from hydrodynamic point of view, this is very intuitive. You can do it right away without any calculations. But I will explain first picture of how I relate this probability to hydrodynamics. Okay, so this is a quantum hydrodynamics. And it gives both classical equations. So if I take this action and then I minimize this, I will get classical equations, but also describes quantum fluctuations, because you can calculate this weight for any u, not necessarily the classical trajectory. And this describes the amplitudes of fluctuations. Right? So next step, I will not explain it in detail, but I will say that to calculate the probability, what I'm going to do is I'm going to do Week's rotation. Namely, I'm going to replace time t to imaginary time tau. Length scale for We will derive it. We will derive it. But you can guess. The only thing you have is the background density. So the only thing dimension here will be rho 0 times r squared e to the minus, and some number. So the question is what the number is. Okay. So if you do this, then your Euclidean partition function becomes integral over u e to the minus s Euclidean of u, where s Euclidean is more or less the same as original s with t replaced by tau, and sign between potential and kinetic energy changed. So this essentially looks like energy of the problem. And again, you remember that rho here is not rho, but rho 0 plus d tau, dxu. So this is considered to be a function of SU, f of u. Okay? So step number 5. So let's solve classical equations for S, which are produced by this action. We'll solve classical equations. With the following boundary conditions, that I want density going to rho 0 and velocity, which means d tau u, going to 0 as x and t go to infinity. That's first. So I want far away from my time equals 0, I want this undisturbed ground state problem, right? With velocity 0 and density equals constant. But most importantly, I want also density as a function of x at time tau equals 0 to be identical to 0 if x belongs from minus r to r. So pictorially, it looks like this. So if this is tau, if this is x and this is tau, yes? Right. True. Yeah. You can. You can. Then what are you going to do with your classical solution? And for this, I need my step number 6. So let me before doing this comment, let me do step number 6 so that the total picture is clear. Step 6 will be consider e to the minus Euclidean action as a function of classical solution, and that's a leading behavior to probability. So the only reason I needed this Euclidean action is just to say that in the Euclidean path integrals, these are probabilities, and the action is minimal on the classical trajectories, which gives maximum of probability. And therefore, for U classical, this is where maximum of probability is. And of course, there is a measure of trajectories around it, but this will hopefully give next order corrections in R. And the leading order will be just substituting classical solution into Euclidean action. Yeah, that's the only reason I needed. Otherwise, I could have just solved classical equations. Okay. And so what will be the solution of those classical equations? How it will look pictorially? Well, let me assume that I'm drawing the density as a function of x and tau, three-dimensional plot. Okay? So what I want is that from minus r to r, this is just 0, right? The density is 0. So on this vertical line, it's 0. But it cannot just form right away. It's solution of classical equations. So the fluid should really part and produce this empty spot. So it will be something like this. So I'm showing only the location of 0 density. So 0 density will not happen instantaneously, but the fluid will just part at some point and will form zero density, and then it should come back again. There will be some fluctuations of density around some particular solution, which one can draw on a computer as a picture. But this is the empty space. This is where rho equals 0. And you are asked to estimate, well, we will compute, but let's first estimate what will be the cost in the action of this type of solution. So if I put this, I know that the absolute minimum of the action is when rho equals rho 0 and velocity equals 0. Then it's just action is 0. So now this one will cost additional action. Let's estimate what it is. Well, roughly the main cost will be here, where the deviation of density is the biggest. And what is the area of this? So this scale is R. What about this scale? Can you guess what the order of this scale is? Like physics. It's no matter, you just have to have some physical intuition. So I have a fluid, and I do some perturbation here, and some waves propagate. So what's the speed of propagation of those waves? It's a sound velocity, right? So I expect that this will be time which is necessary for sound to propagate the distance of the order of r. So this will be something like r divided by Vs, okay? Where Vs is the sound velocity. Well, Vs is related to rho 0, it's proportional to rho 0. This is depends on just background density. But what's important here is that the typical scale here is of the order of r, okay? And this is of the order of r. So the area is of the order of r squared. And this is why you have here r squared. The typical actions that you will obtain will be scaling as r squared, because you also have time direction. One interesting comment, which I wanted to make at the end, but it's important, so I will make it right now, is that suppose that I have now finite temperature. Let's generalize, yes. This is I derive classical equation, and I ask, label all points on a xt plane where rho is 0. Here it's 0, rho is 0 just everywhere here. What I'm saying is that to have 0 on this line, which is what my boundary condition is, I really need to have 0 slightly before that and slightly before that. So rho is actually 0 here. And outside is complicated. I can show you the picture afterwards, but it's complicated. But here it's just purely 0. So what I'm saying is that the scale of disturbance of the background vacuum solution is of the order of r squared, the area of the r squared. So I expect that the action cost is e to the minus r squared. Okay, now let's see what changes in finite temperature. And at finite temperature, the simplest way to do that is just to say that time runs from 0 to beta with periodic boundary conditions. So essentially, I'm on a cylinder now. Well, let me make it from minus beta over 2 to p. So timing 0 is here. Okay? So essentially, it's a cylinder. So I have to identify this line. So, and again, I want to have my emptiness here from minus r to r. I solve classical equation and I obtain something like this. And its scale is e to the minus r squared. But now let's assume that I increase r and make it like this. Then it's pretty clear that it will be something like this. So one of the r's will be replaced by inverse temperature, by beta. Okay? So instead of e to the minus r squared in purely quantum case of low temperatures, if temperatures are finite or if r is big, then you'll get something like e to the minus r divided by temperature. Because one of r's is replaced by beta, and beta is 1 over temperature. And this is where our typical intuition comes from statistical mechanics. When I ask you about air, this is what you usually remember, that it's exponential, because we usually deal with statistical fluctuations, not quantum. With quantum fluctuations, extra dimension, which is time, is added to the system, and therefore the scale of r becomes r squared. So if I ask the question about emptiness in the air, it will be e to the minus r cube, minus volume. If I ask the same about some quantum fluid, like at 0 temperature, then it will be e to the minus r force. That's additional dimension, I said. Okay, any questions? So let me now, I have about 5 minutes to complete the calculation, which I know how to do because you can always leave it as an exercise, which I'm planning to. So basically, the ideology is very simple. Solve those classical equations, substitute the classical solution into the Euclidean action, e to the minus s will give you the leading order. So basically, we finished here. Well, let me say a few words about actual solution. So we take equations dt rho plus dx rho v equals 0, dtv plus dx v squared over 2 minus pi squared rho squared over 2 equals 0. The only change to what we considered before is this minus. This is due to the weak rotation. And what I'm going to do is I'm going to introduce complex variables. And this is now we're going back to the comment before. Now it's after weak rotation, so complex analysis will be important. Let me introduce the following variable, I rho plus iv. Immediately recognize that this is analytical continuation of my k right, k left used before. So before weak rotation, it was pi rho plus v or minus pi rho plus v. Right? Now it's iv. And I can rewrite equation for w as dt w minus I w dx w equals 0. And nice thing about it is that if you just plug it in here, and the real part of this equation will be continuity equation, and imaginary part of this equation will give you Euler equation. Similarly to how we get ut plus ux before. This is the imaginary version of that. Same. Then it turns out that you can write explicitly this solution in a very simple way. Just write that w equals f of z, where f is any analytic function of z, and z is x plus I wt. Okay. Exercise, check that if you take any analytic function f of z, and w equals to this, you see implicitly, because w is also inside the argument, so then w satisfies this automatically. Okay? If we are far away from this disturbance, then far away velocity becomes 0 and density becomes rho 0, so w becomes actually constant, real constant. Then z is essentially x plus it, just complex space-time variable. But close to the disturbance, it's significantly different. So this is z is not just simple plain complex space-time variable. Okay? So so this is a general solution of this equation. Now we have to find particular solution which also satisfies EFP boundary conditions, namely those. Right? And I claim that this is given by w equals f of z, which in this form has pi, in this case has form pi rho 0 z divided by square root of z squared minus r squared. This simple analytic function has give you solution for EFP problem for free fermions, for Z hydrodynamics. It's very easy to see. Suppose that z goes to infinity. So x and t goes to infinity, z goes to infinity. This becomes 1, w becomes pi rho 0, which means that rho equals rho 0 and v equals 0. And therefore, this solution satisfies this part of boundary conditions. Also, suppose that time equals 0. Actually, I should use tau here to be consistent. Suppose tau equals 0. Then notice that z is just x in this case. And f of z, so w, becomes pi rho 0 x divided by x squared minus r squared. If x is bigger than r, this is real, which means that velocity equals 0, but density is not. If x is smaller than r, this is purely imaginary, which means that velocity is not 0, but rho is 0. And rho equals 0 is precisely what we want in our second boundary condition. So what I'm trying to say is that this is the solution. This is the optimal fluctuation, which the optimal fluctuations of this quantum one-dimensional fluid, which gives you empty space from minus r to r at time equals 0. Okay? Any questions? I think so, yeah. You can show uniqueness by usual arguments that let's take another one which satisfies everything else, let's take the difference. You can show that. Yeah. Okay, so this is the optimal fluctuation, and then we substitute this solution into the action, into Euclidean action here, and compute it. And we obtain that Euclidean action of U classical, of the solution given by this formula, is actually equal to is equal to 1/2 pi rho 0 r squared. So the leading Gaussian asymptotic is e to the minus 1/2 pi rho 0 r squared. If you remember that pi rho 0 is actually k Fermi, then this is just k Fermi r squared. And the only thing we worked for is this coefficient 1/2. So, actually, if you just substitute this into this action and calculate, this is some work. It's really exercise. It turns out that there is a tricks of how to do it much more effective way. Well, and this is based on the fact that if you substitute, so if you, the variation of that action on that trajectory is 0, because we looked for the optimal one. So if you, for example, take a derivative of that action with respect to r, it turns out that for that derivative, everything else cancels except for boundary term. And the boundary term is basically asymptotics of the solution. It turns out that it's possible to express this coefficient explicitly in terms of the asymptotics of the solution at large C, which is much easier. So you just basically find the asymptotics, substitute. It's very easy. So, but I leave this all as an exercise. Okay. So you can find explicit forms for rho and v. I'm already over my time. So you can find explicit forms for rho and v. It's nice that this diamond has actually precise analytic formula. It's called asteroid. It's x to the power 2/3 plus pi rho 0 t to the power 2/3 equals r to the power 2/3. So you can derive that. And you can derive many other things. And one last thing which I wanted to say is that there is a class of problems which are recently being called Arctic Circle problems. It's about solving some dimer tiling models with given boundary conditions. And dimers can be reduced to free fermions, so you can actually use all these techniques there. And as I said, there is nothing special about these techniques about free fermions. In principle, you can be formulated for any either integrable or non-integrable model. There are problems in actually implementing this and finding solutions explicitly or implicitly and so on and so forth. This is not done. Thank you. Yes.
Can you actually find the contour of that empty region from that function?
Yes. Yeah. No, I have a explicit formula for rho v, everything, and I have plots of rho and v in its function of x. I can show this later. It's just hard to reproduce on the blackboard. Yeah, Siram.
So can you calculate this object for Laughlin wave function? Have people calculated it?
Yes, you can. Yeah, this is generalizable for Collisionless model easily, and well, not Laughlin, but one-dimensional Laughlin, which is the ground state of Collisionless model. Then it's just exactly the same up to some factor.
You can take a Laughlin wave function and stick it in that form.
In principle, yeah. Nothing one-dimensional in the general method as well. If you have high-dimensional hydrodynamics and you ask what's the big optimal fluctuation and what's the leading probability, you can still do weak transform and solve it and find it. So in principle, yes. I didn't do that.
Has anybody done that?
I think the emptiness formation for Laughlin is known, but not this way probably. So I'm not sure. Interesting.
Maybe we should continue over coffee. Let's thank Sasha once more. Please be back at 11:30.